Good morning, IB Math. All right, as we continue Chapter 6, today we're going to look at 6b, which is surface area of 3D shapes using a little differential calculus. Now, if you're still a little bit nervous about the calculus, don't let it give you a hard time. We're not going to get really into deep stuff. It's more concept-y type stuff here. All right. Before we actually start, I want to talk about the whole 3D and the dimensions. Let's talk about dimensions first. 0 dimensions. Is there anything that has 0 dimensions? Yes, a point. For example, let me do the examples in a different color. For example, point A. Now, point A has no dimensions. A point has no length, no width, no depth, no height, no breadth, no nothing. It's 0 dimension object. It's the only 0 dimensions. It has no dimensions at all. And then we get into 1 dimensions. What's an example of 1 dimensions? Something like a line. Line AB, and this is point A. Oops. Line AB. So if I take a point and push it in a direction that it's never gone before, I get 1 dimension, length. A line is a 1-dimensional construct. All of our segments, parts of figures, are 1-dimensional constructs. 2 dimensions. And I want you to think about a plane, a flat surface. Usually we indicate a plane with something like this, and we call it like capital Q. And I want you to think about it as a flat surface. It has length and width, but no depth. Even a piece of paper, if I take just a simple piece of paper, even a piece of paper has got some sort of width here. If it had no width, or depth, if you will, and I have just length and just width, then that would be really 2 dimensions. And then, of course, 3 dimensions. And right now, I'm going to use the term solids. So if I draw a 2D representation of a 3D object, so here's what is that, orthographic projection of a cube, a 3-dimensional object. Now notice that I'm drawing everything in 2 dimensions. A line has no dimensions. If you push a line in a direction it's never been before, you get, a point, I'm sorry. A point has got no dimensions. If you push a point in a direction it's never gone before, you get a line. If I take that line, which only knows length, and push it in a direction it's never gone before, I get width. I get 2 dimensions. If I take something 2 dimensions, now 2 dimensions has got length and width. And if we were living on a flat surface, we could look all 360 degrees around, and we might think that we can see everything 360 degrees. But if you can take that flat surface and push it in a direction it's never been before, in other words, that way, then you get a 3-dimensional object. 3 dimensions are solids. Now, how many points exist? Well, there's an infinite number of points. How many lines exist? Well, there's an infinite number of lines. How many planes exist? Well, there's an infinite number of planes. How many solids or space exists? Only 1. Doesn't seem right, does it? We live in 3 dimensions. We have length and width and breadth. We have 3 dimensions we live in, and it's called space. The solid is an example of a figure in 3 dimensions that has 3 dimensions. There should be infinite number of spaces, right? And now we kind of get into science fiction and philosophy and quantum physics. And what about the 4th dimension? No, I'm sorry, the 4th dimension is not time, but just like all of these objects, if we, who are living in space, could turn and look in a direction that no one has ever looked before, we would see the 4th dimension. Just like all of these things. If I could take somebody that lived on a plane and tell them to look in a direction they've never looked before, they would see 3 dimensions there. So kind of cool stuff. Really, this should be a 12 to 15 minute kind of tangent conversation, talking about it and interest, and maybe moving it into the world of TOK and who knows, exploring it and having some fun with it. But unfortunately, we're just going to move on. No time for that kind of fun discussions. I miss that, especially with you guys. You guys are very clever, very, very, very quick, very sharp. All right, so I want to take a look now at some of my two-dimensional or my one-dimensional constructs, my lines, and things like something as simple as let's think about a circle for a moment. Now, a circle, how many dimensions does a circle have? 2, length and width. But within a circle, I've got, let's see, I'm going to use the radius here. The radius, what kind of construct is that? How many dimensions does it have? Only 1, length. And we know that the circumference of a circle is pi times diameter. I'm going to write 2r. Circumference is 2 pi r. But I want to think about this a little bit differently. That's my circumference. Now I want to think about the amount of stuff inside the circle, the area. Okay. Now, when we first studied circles, the important measurements were things like the diameter, the radius, and the circumference. And those are all 1 dimensions, and those are all, we use pi. Pi is the ratio. If I solve here, circumference over diameter, or circumference over 2 times radius is pi. It's a ratio of the circumference to the diameter of a circle. Now, the area is the amount of space inside of this 2-dimensional shape we call a circle. Once we define this, area we define as pi times radius squared. We can imply a very important relationship between the area and the radius, and the circumference could be inferred. In other words, the circumference, if I think about combining these, is going to be the change in area over the corresponding change in radius. Okay. So this can be implied from these formulas here, that the circumference, change in area, over the change in radius. We have a better way of writing that. Change in. What do you think of when you think of change in, right? We have a, I know you're thinking triangle, right? But no, we're beyond that. So we're going to say that the circumference can be written as dA dr, the change in area over the change in radius. Now, this is a 2-dimensional shape. What about if we have a 3-dimensional shape? What would a 3-dimensional circle look like? It would be this is a circle. A 3-dimensional one would be a sphere. And let's see, how do we draw a sphere? We draw one axis, the hidden axis, another, and the hidden axis. And then just to use a different color for the radius. There's my radius. So when we talk about a sphere and what is the area of a sphere, what we're really talking about is the surface area of a sphere. And the surface area can be expressed as the change in the volume with respect to the change in the radius. The change in the volume over the change in the radius. Notice how each time we go up, each time we go up a dimension, we go up in the dimensions here as well. All right, so there are some formulas that we need to know here. I know all the formulas are in your formula booklet. You'll be able to use them there. But as we're working on things, there are some formulas that you really should know. So these are formulas, and you'll notice that a lot of the stuff that we're going to do in this chapter, a lot of it comes from concepts from geometry. Like I keep saying, if you've had pre-calc, you're definitely going to be ahead of the curve in here. So let's talk about a pyramid for a moment. So the formulas, if I have a pyramid, oh gosh, that's not a very good pyramid, is it? The volume of a pyramid is 1/3, and we wrote it BH, where B is the area of the base, and H is the true height of the pyramid. This, H. And then this is B, the area of the base. So if it's a rectangle, it would be length times width. If it's a square, side squared. If it's a hexagon or whatever it is, the area of the base times the height is the volume of a pyramid. In a cone, oh, I should name them too, shouldn't I? So here we have our pyramid. Here we have the cone. In a cone, the volume of a cone is 1/3 BH, where B is the area of the base. H is the true height. A cone is just a special type of pyramid. In fact, the base is a circle. So it's 1/3. The area of a circle is pi r squared h. Pi r squared times h. Now notice on the cone, we also have this length here, the slant height. I'm going to put an S. We also have the slant height of a pyramid. And the slant heights come into account when we talk about the surface area. In fact, let's do that. The surface area of a cone is going to be the area of the base, which is pi r squared, plus this the shape going around there, like an ice cream cone, the shape of an ice cream cone, which is pi r s, pi times the radius times s. I know s is horrible, but there we go. We're stuck with it for the slant height. Similarly, it's going to be the same thing for the pyramid. The other shape that we need to know is the sphere. So let's take a look at the sphere. The sphere, interestingly enough, only has one measurement, just the radius. And the volume of a sphere is 4/3 pi r cubed, and the surface area is 4 pi r squared. The interesting thing here is, if ignore that for a moment, if I took the surface area, and if I took the volume, and then I took the derivative of the volume, what would the derivative of the volume be? Move the 3 down here, make it a squared, cancel the 3's, 4 pi r squared. And that's not by accident that happens. All right, so those are the 3 main formulas, the things we're going to be looking at. We're going to see some other things along the way. For example, we might see something called a hemisphere. And don't let a hemisphere give you a hard time. A hemisphere is literally just half of a, oh gosh, that's an awful picture, isn't it? It's just half of a sphere. So what would the volume be? Well, 1/2 of this. What would the surface area be? Is it just as simple as half of that? No. Why not? Well, if I take half of that, I'm going to get the surface area of the bottom part. But what about this flat part here? It would be half of that plus this circle, plus pi r squared. So watch out for that. Something else we're going to have to deal with too is something called composite figures. Composite solids. And a composite solid, for example, might be something like a cylinder with a cone atop it. A cylinder and a cone. A big pencil, big bullet, I don't know, something like that. And when we talk about volume, well, composite figures are easy. Volume is just going to be the volume of the cylinder plus the volume of the cone. The volume of a hemisphere is half the volume of the sphere. But watch out for surface area, because it's not just going to be the surface area of the cylinder plus the surface area of the cone. It's going to, if I think about the total surface area of this composite figure, it's going to be the base of the cylinder plus the lateral face of the cylinder, but not the top of the cylinder. And then as far as the cone goes, not the bottom of the cone, just the lateral face of the cone. The bottom of the cone and the top of the cylinder are actually inside and not part of the surface area. So we're going to have to be very careful when we're dealing with these types of things, composite figures. All right, I've got one sample problem for you, and then I'm going to give you a chance to do 6.B. Let's say I have a cone and I'm going to tell you that the circumference of the base of the cone is 40 centimeters. And I'm going to tell you that the volume of the cone is 4.8 liters. Let me write that out, because this gets tricky. We have to deal with the metric system, and the rest of the world does. So when all of the other students in the world see this, they already know 4.8 liters, how many cubic centimeters that is. And here in America, we don't know the metric system very well. So this is definitely going to be an issue, converting things back and forth. For example, I know I'm going to deal with centimeters here, the circumference. I'm going to work backwards to find the radius and all that other good stuff. But 4.8 liters, do we know how many cubic centimeters that is? Well, 1 liter equals 1,000 cubic centimeters. So 4.8 liters is going to be 4,800 cubic centimeters. And I know this is in the formula book, but students in the rest of the world, they use the metric system. They're very comfortable and familiar with it. It's going to be a bit of an issue for us. All right, so what do I want to do with this? Let's find the ratio between the height and the radius, and then find the capacity, given that ratio, find the capacity of a similar cone that has a radius of just 15. All right, here we go. So I know that circumference equals 2 times pi times the radius. If I solve that for radius, I'm going to get, divide both sides by 2 pi. My radius is going to be circumference over 2 pi. So my radius is going to be 40 over 2 pi. Okay, or 20 over pi. And I'm going to leave it like that. That's the radius of that cone. Okay, so now to find the volume, I'm going to use the volume formula for a cone, which is 1/3 pi r squared h. Did I say cone or did I say pyramid? It's a cone, right? This is a cone. 1/3 area of the base, it's a circle, pi r squared, times h. All right, substituting in, I know the volume. It's 4.8 liters, which is 4,800 cubic centimeters, is 1/3 pi times my radius is, I'm going to leave it as 40 over 2 pi. 20 over pi would be better, and make it a little bit easier, but I just want you to see in your notes where that came from, times the height. Now I want to solve this for height. All right, so let's see. Let's do a little bit of work here. 4,800, 1/3 pi times 40 squared, 1,600 over 4 pi squared times height, 1600, the 3, and the 4 is 12. Let's see, 4800 equals 1600. One of the pi's are going to cancel here, over 12 pi times h. Solve for h, and I'm going to get h equals, multiply by 12 pi, divide by 600. On the calculator real quick, I think I get 36 pi. Solving for that, 36 pi. All right, so the next part of this is I want to know the ratio between height and radius. Find the ratio between height and radius. Let me move that out of the way. Move things up here. All right, so height over radius is going to be, let's see, what was it again? The height, 36 pi over the radius of 40, and I think it's going to simplify to 9 pi squared over 5. All right. Next part. I want to, so that was the first part. Second part, find the capacity. Ooh, what does that mean? Find the capacity. Yeah, volume, right? Volume. Find the capacity of a similar cone, which has a radius of 15 centimeters. So our cone had a radius of 20 over pi centimeters. A similar cone means that it's going to be, well, think about what the definition of similar means. All the angles are going to be the same. It's just going to be larger or smaller. So we didn't know the height. We could work backwards to find the exact height here. All right. So let's see. Height is going to be 15 times that 9 pi squared over 5, which gives me, that's 25, 3 times 9, 27 pi squared for the height. All right, so what's the volume going to be? Find the capacity. Capacity is volume. Volume of a cone is 1/3 pi r squared h. Substituting in, I'm going to get 1/3 pi times 15 squared times 27 pi squared. My new radius of 15, my new height here. Oh gosh, let's see, 15 and 15, 225 divided by 3 times 27. On the calculator, I think you get 2,025 pi. Oh, this is weird. Pi squared and pi cubes. 27 divided by 3 is 9 times 225, 20. Okay, there we go. So, oh gosh, let's see. Now I need to convert this back. So if I write this out as a decimal, oh, I can't do that in my head. That one I definitely can't do in my head. All right, so let's see. Calculator, where are you? 25 times pi cubed. I'm getting 62,787, and that's cubic centimeters. So last thing I want to do is I want to put this back to liters. So one of the reasons that the metric system is so nice is 1,000 is 1 liter. So my final answer is going to be 62.0 0.79 liters. There we go. Hopefully you've been using the metric system in your other classes. It is a much nicer, easier system. I could tell you stories about how I knew the metric system when I was a little kid in England, and when I moved to this country when I was 13, I had to learn the American system. Oh gosh, it was very frustrating. Feet and yards and inches. None of the numbers seemed to make sense. It was all weird stuff. Miles, we kind of had an idea for miles. A lot of the old folks in England still used miles. But then liters, gallons, cups, pints, quarts. Oh my goodness, very, very confusing. Very, very confusing. All right, ladies and gentlemen, I want you to go do assignment 6B. It's on page 377, and I want you to do numbers 1 through 6. And that's where I'm going to stop this video. And then, as I said, I'm going to chunk up this whole chapter into just doing one section at a time. In class, we would be doing 2 or 3. But we're just going to do one video per section as we go through. All right, so good luck. If you have a hard time with any of the problems, put something in the post section saying, oh, I didn't understand problem number 4. Can you explain problem number 4? And ladies and gentlemen, if you see somebody posting with a problem, then and you want to answer it, then go ahead and reply to them. And write your answer out. Do all the work out on a piece of paper, and then just upload it as a document, either as a JPEG or a PDF. When you're sending me your homework, remember, send them to me as a PDF or JPEG. Take pictures of them. And just one assignment. Just A is its own assignment, B is its own assignment. I know the homework sheet that I uploaded is the regular homework sheet. I think I said this when I finished A as well. I just want to make sure that we're just doing one section at a time. So just do B, get it done, and get it turned into me. I'll talk to you again soon. Bye.